On the 26th of April 1882, many of the leading scholars and scientists of Britain, a nation at the height of its global power, filed into Westminster Abbey to lay Charles Darwin to rest. The celebrated naturalist who changed humanity's understanding of evolution and the origins of the species had died a week earlier at 73 years of age. He was being laid to rest in a place which was typically reserved for royalty, but which had a growing spot in the Abbey known as Scientists' Corner. The tradition of burying England's greatest scientists here had commenced 155 years earlier when Isaac Newton was laid to rest in the nave. Now Darwin joined him there. These were, and arguably still remain, the two greatest scientific minds to have emerged out of England. Beginning in the mid-1660s, as England was ravaged by plague and London burned to the ground in the Great Fire of 1666, Newton began revolutionizing human knowledge about the physical world, establishing the laws of gravity, before then moving on to transform our understanding of everything, from optics to calculus. His Philosophiae Naturalis Principia Mathematica, published in 1687, has been termed the greatest work of scientific study ever written. 172 years later, Darwin's On the Origin of Species appeared in print, explaining in clear terms how human beings and other species evolved gradually over millennia. In another coincidence, both men's greatest works were actually published over 20 years after the foundational research within them was actually carried out. Newton's Principia was based to a large extent on discoveries he made in the mid-1660s, while Darwin had waited a quarter of a century to publish his findings from his famous voyage around the world on board the HMS Beagle in the 1830s. Two men, two much-delayed books that revolutionized the history of science and the world, and two resting places mere feet away from each other in Westminster Abbey. This is the story of Isaac Newton and Charles Darwin. It is 1666, and England is in crisis. The dreaded plague is spreading north from London. The universities close, and both students and teachers head home to safety, and one such student heads north to his family's estate in Lincolnshire. One afternoon, while sitting drinking tea, he observes an apple fall to the ground and begins to speculate about why all objects are drawn to the Earth's center. Eventually, nearly 2 decades later, the same man publishes his Theory of Universal Gravitation, which, for the first time, lays down the laws of gravity and simultaneously revolutionizes mathematics, physics, and astronomy. His name? Sir Isaac Newton, history's greatest scientist. The man known to history as Isaac Newton was born on Christmas Day, the 25th of December, in the year 1642, at the manor house of Woolsthorpe, south of the town of Grantham, in Lincolnshire, in the East Midlands of England. The Julian calendar was still in use in England at the time, and it was the 4th of January 1643 on the continent, where most countries had adopted the Gregorian calendar that was 10 days ahead of the Julian calendar. Little Isaac was clearly sickly and underweight, and it is understood that his mother believed he would die shortly after being born, a development which explains why he was not baptized for a week after his birth, a ceremony which usually took place within 48 hours of the birth. Whatever the circumstances, Isaac pulled through and survived. He was named after his father. Isaac Newton Sr. was a landholder and an important farmer in rural Lincolnshire. The family's wealth was indicated by the fact that they lived at Woolsthorpe, a substantial enough manor house. The Newton family had built on generational upward social mobility here from the early 16th century onwards and had become prominent members of the yeomanry by the middle of the 17th century, the equivalent of being middle-class farmers. Isaac Sr. was uneducated and illiterate, a not uncommon state of affairs for middle-class yeomen in the 17th century. Isaac would never know him. His father died in early October 1642 at 36 years of age, 2.5 months before his one and only son was born. He left behind a sizable enough estate and a range of livestock that included 4 dozen cattle and 235 sheep. This wealth would have a bearing on Isaac's life and allowed him to pursue a life of scholarship in later years. Isaac's mother was Hannah Newton, the daughter of James Askew, a member of the gentry from the town of Market Overton in Rutlandshire. It is a sign of Isaac Newton Sr.'s upwardly mobile nature and economic success that he had married Hannah, whose father was of a higher social status than the Newtons. She eventually remarried after her first husband's death. Her second marriage was to the Reverend Barnabas Smith, a churchman with a large estate that generated an income of around £500 per year, a substantial amount of money in the middle of the 17th century. When she married Smith, Isaac's mother left to live with him at North Witham, around 3 kilometres away from Woolsthorpe. There she started a new family. Isaac was not a part of it. When his mother headed to live with Smith, she left her firstborn son with her parents. Evidently, Isaac's childhood with them was not a pleasant one. Years later, when his grandfather died, it was revealed in his will that he had left Isaac nothing, suggesting a frosty relationship. In all of his extensive correspondence over the decades, which has all been analysed in detail by historians, there is no mention of his grandfather Askew, and his grandmother was not exactly spoken of glowingly by Isaac on the few occasions in which he mentioned her. Finally, it has also been speculated that Isaac grew to loathe his stepfather, the Reverend Smith, an understandable development if he felt abandoned by his mother and was left to grow up in a house where his relationship with his grandparents was strained. Historians have concluded that the peculiar elements of Isaac's later personality, his aloofness and distance from others, were shaped by these early childhood experiences. Newton's life was also influenced greatly by intellectual, cultural and social forces which had commenced well over a century before his birth. The Renaissance is typically viewed through an artistic prism as a movement that led to the emergence of great painters, sculptors and architects. In reality, it transformed every sphere of European life in the 15th and 16th centuries, from philosophy and diplomacy to commerce and technology. One of the offshoots of it was the scientific revolution. Medieval European science was primitive. A certain amount of knowledge about astronomy as well as biology, mathematics and the natural sciences had been retained from the ancient Greeks and Romans. Yet, in many spheres, European scientific knowledge was remedial in medieval times. That all began to change in the early 16th century. First, a Polish man, Nicolaus Copernicus, published a book entitled On the Revolutions of the Heavenly Spheres in 1543. In this, he laid out the heliocentric model of the universe, which stated that the Earth rotated around the Sun and that the Earth was not the centre of existence. Copernicus's work opened the floodgates for a wave of new scientific inquiry. Soon figures like Tycho Brahe in Denmark, Johannes Kepler in Germany, and Galileo Galilei in Italy were conducting groundbreaking work on astronomy, optics, mathematics, and physics. They also began developing scientific instruments like telescopes and measuring tools. The scientific method emerged too. This was the idea that a person could come up with a hypothesis and then test that through experimentation and reasoning. This work was related to philosophical inquiry, which had long used such methods going back to the ancient Greeks. It was also in ancient Greece that philosophers began conceiving of the world as being made up of tiny particles which they had called atomos, the root of the modern word atom. In line with this, the scientists of the European scientific revolution viewed themselves as being natural philosophers. There was an English dimension to all of this, though the scientific revolution arrived at England later than most other parts of Western Europe. One of the earliest proponents of the new science was Sir Walter Raleigh, the famous Elizabethan courtier. Raleigh fell out of favour after Elizabeth's death and was imprisoned in the Tower of London for 13 years between 1603 and 1616 by the new king, James I. There he set up a laboratory and spent much of his time carrying out experiments. Elsewhere, the drive to discover the northeast and northwest passages to Asia by sailing north of Europe or America had led English navigators to develop scientific instruments and accomplished cartographic or map-making skills in the 16th century. But it was really in the 17th century that England came into its own as a centre of the scientific revolution. The Lord Chancellor of England between 1617 and 1621, Sir Francis Bacon, was known for his contributions to the scientific method and inductive reasoning. William Harvey, an English physician of the early 17th century, conducted groundbreaking work on the circulatory system and human anatomy. By the time Newton was born, Robert Boyle, the youngest son of the first Earl of Cork, Richard Boyle, was commencing his pioneering work in chemistry. He is now deemed to be the father of modern chemistry. There were many other natural philosophers beginning to make contributions here and there to the various fields of science. All of their activities gained greater coherence and collegiality in 1660, when the Royal Society was founded in London as a means for scientists to swap ideas and correspond about their research. Newton would soon emerge as the greatest figure of the scientific revolution in England. Not much is known about Isaac's earliest years. He was reluctant to write about his childhood and later life. His stepfather died in 1653 when Isaac was 10 years old. His mother then returned to Woolsthorpe along with Isaac's younger 3 half-siblings. By then, Isaac's education was already well underway, guided by a cousin, another churchman, named Richard Askew. In 1655, when he was 12 years old, he was sent on to a grammar school in the nearby town of Grantham, where he was taught by a Mr. Stokes. The curriculum would have had a heavy emphasis on learning Latin, and then that stemmed outwards into the subjects that were written about by the greatest Latin writers, namely Roman authors like Cicero, Quintilian, Virgil, Tacitus, Seneca, and the like. The subjects were rhetoric, history, prose poetry, and philosophy. Still, recent research has revealed that Mr. Stokes did have a good bit of mathematical knowledge too, and Newton's abilities in this area were consequently fostered from around age 12 or 13. Isaac, who would notably display almost no interest in the opposite sex as an adult, appears to have had a teenage romance with the stepdaughter of a Mr. Clark with whom he lodged at Grantham. In 1659, when he was 16 years old, he was recalled home to Woolsthorpe to help out on the family farm, but this was a short-lived experiment. Isaac hated farm work, and both Mr. Stokes and his cousin Richard Askew had learned enough about his intellect to realise that he had the makings of a gifted scholar. They organised to help finance the finishing of his elementary schooling, and then, with this done, he was sent off to Cambridge University in 1661. Newton's earliest years at Cambridge were formative in his emergence as one of the greatest scientific minds in human history, though often in unusual ways. His comparatively humble background meant that he was assigned as a sub-sizer. This meant he was expected to earn his keep cleaning the college and was not allowed to dine with the other wealthier students. This suggests his mother had refused to provide much financing from the estate she now controlled from not one, but two deceased husbands. What it did ensure was that Newton was somewhat socially isolated as a lowly sub-sizer, something which encouraged him to focus more on his studies. Early on, he was taught by Benjamin Pullin, a tutor who assigned him lots of writings by the giant of the medieval scholastic curriculum, the ancient Greek polymath Aristotle, a man who is primarily remembered as a philosopher, but who was also one of the great early natural scientists. Before long, Newton was moving on to more contemporary scientific works and had developed an especially keen interest in physics. About 2.5 years into his studies at Cambridge, he then abandoned any sense of formal or structured learning. His lengthy notebooks, which have survived down to the present day, show that he stopped reading the works of Aristotle and other canonical Greek and Roman works by figures like Plato. Instead, Newton began to concentrate overwhelmingly on more modern scientific, philosophical and political writings. Robert Boyle's pioneering chemistry work featured amongst what he was interested in, as was Thomas Hobbes' great work of political theory, Leviathan, published just a few years earlier in 1651. However, it was the works of Galileo that held Newton's attention above all others at this time. The Italian polymath had revolutionized the study of astronomy, optics, and many other fields in a series of studies carried out between the 1590s and 1630s. Decades later in England, they were inspiring Newton to break with the established curriculum at Cambridge and begin his own highly original research on mathematics, physics, and optics. Newton's education at Cambridge was coming to an end just as a series of events in England would create an ideal environment for him to carry out one of the most miraculous periods of research and writing ever undertaken in the history of science. Late in 1664, a large comet was seen over southern England. In the minds of early modern English people, this was a celestial portent of bad times ahead. Early in 1665, their worst fears were confirmed when a virulent wave of the bubonic plague struck England. While the plague's most terrible moment had come in the late 1340s and early 1350s, when it killed upwards of 1 out of every 3 Europeans, smaller waves of the disease struck the continent periodically for centuries to come. Crowded, dirty cities were particularly susceptible to plague pandemics, and these outbreaks even reached the streets of relatively small university towns like Cambridge. For instance, an outbreak of the disease in 1603 had killed an estimated 25,000 to 30,000 people in London, over 10% of the whole at the time. There was no cure or no effective way of fighting it other than to flee from urban areas and avoid contact with others who carried the disease. Thus, when the plague arrived, the wealthier people who were able to do so often fled from London, Bristol, Cambridge and Oxford to their country houses and spent months there. This is what happened in the plague year of 1665, a particularly destructive wave of the disease which killed upwards of 100,000 people in London in the mid-1660s, about 15% of the total population there at the time. Cambridge University closed, and Newton retreated to his family estate at Woolsthorpe. The isolation and lack of interruption would allow him to produce an enormous array of work, such that this period in 1665 and 1666 is often termed Newton's Annae Mirabilis, or miracle years, much like that which Albert Einstein had centuries later in 1905, when he published 4 papers within the space of a few months, which revolutionized the study of physics. Newton's work in his miracle years can broadly be broken down into 3 key fields: physics, mathematics, and optics. Despite the tendency to view this as a period of miraculous discovery, Newton was building on work he had been carrying out during his years at Cambridge, and which he had kept extensive notes of in a book which he inscribed with the title Quaestiones Quaedam Philosophicae, meaning certain philosophical questions, though the topics covered were concerned with the hard sciences. His first major discoveries were mathematical. They resulted in the development of the binomial theorem in 1665, a mathematical concept which allows for expansion of much more basic theorems like x plus y. This was the foundation for further work which involved measuring large objects and their movement, as well as algorithms for tracing curves, tangents, and the like. No other mathematician in Europe had ever arrived at findings that were this complex before. They laid a lot of the basis for the development of modern calculus. Newton's response to making these discoveries was to record them in a paper which he entitled, "To resolve problems by motion, these following propositions are sufficient." He then placed the paper in a drawer and forgot about mathematics for at least 6 months. He would not make any effort to publish or disseminate that work at the time. With this done, and still mired in his continuing self-imposed exile from the plague, Newton moved on to studying mechanics. His mathematical inquiries were related to this, as basic study of weights, measures, and mechanics requires use of mathematical equations. Newton wanted to build on the work of Galileo and René Descartes in this area, the latter a philosopher who 30 years earlier had come up with the famous phrase, cogito ergo sum, I think, therefore I am, as a basis for an objective, unquestionable truth that could form the foundation of a philosophical system. Building on their work and using his own complex mathematical abilities, Newton now began to work out a new theory of how gravity functions. By studying how objects collided, he worked out that objects of any kind exert force over one another when they clash or meet. This sends them in different directions, but there is evidence of a center of gravity along a straight line. Experimenting further, he came to the conclusion that particles or atoms attract one another, and that the force involved in this gravitational pull correlates with the mass of the objects in question and the distance between them. It is a complex concept and was tied into several other conclusions he reached in his notebooks in 1665 and 1666 about how force, gravity, and mechanics operated. The simplest of these laws of physics which he devised at the time is the third law he wrote about. This states simply that every action has an equal and opposite reaction. When you jump into the air, this action is immediately followed by gravity pulling you back downwards to the ground by the same distance. While some of the laws concerning mathematics and gravity which he devised at this time were consequently more complex than others, what they amounted to in their entirety was a fundamental expansion on human understanding of how gravity and motion work. A fanciful story later developed that Newton had reached his conclusions about gravity after seeing an apple fall from a tree at Woolsthorpe. The tale was probably supposed to mimic a story about the ancient Greek mathematician Archimedes making one of his great discoveries while taking a bath and discovering the principles of buoyancy and displacement in the process. In the long run, Newton's discoveries around gravity, weights, and mechanics in the mid-1660s were the most important. There was a third field, though, beyond mathematics and hard physics. Newton also made some important discoveries in the field of optics at this time, the study of light, colours, and the visual world. From this, we can get a sense of how Newton carried out his research and experiments. He wanted to see if the rays emitted by different colours could be perceived in different ways. To achieve this, he first painted one end of a piece of thread red and the other blue, and then observed them through a prism. They looked disjoined, as he had expected, demonstrating what's known as the heterogeneity of light, the fact that light can appear more intense and available depending on different sets of circumstances. He then expanded the research by setting up a dark room through which he only allowed in a narrow beam of light. Then he placed a prism in front of the beam and refracted that onto a wall that was over 20 feet away. The resulting colour spectrum was 5 times longer than it was wide. What Newton consequently realised was that light was not homogeneous, but heterogeneous. It is not made up of one single thing, but is instead comprised of different parts which can be seen in terms of the different colours in a light prism. This is the corpuscular theory of light, as Newton would describe these parts which make up light, as corpuscles. This research would become the foundational basis for Albert Einstein's subsequent discovery of photons nearly 2.5 centuries later. By the time 1666 came to an end, Newton had made a series of breakthroughs in the fields of mathematics, physics, and optics. Nobody as yet, though, knew what he had accomplished. His remarkable findings were carefully recorded in his notebooks at Woolsthorpe, but he had not yet shared them with the world. It was the spring of 1667 before it was considered safe to return to Cambridge, as life in southern England was so disturbed by the final stages of the plague year and the Great Fire of London that had destroyed the capital in September 1666, leaving around 100,000 homeless, people who either encamped outside the ruins of the city or dispersed to other towns and villages around the country. In this atmosphere of disordered life, Newton arrived back at Cambridge and managed to gain election as a Fellow, a post that provided him with a modest salary. He began teaching, tutoring and continuing his research back at Cambridge. He also started to disseminate some of his findings in a limited way. For instance, he distilled some of his mathematical work into a tract entitled On Analysis by Infinite Series, which he then gave copies of to a number of colleagues. This was hardly the greatest example of academic self-promotion ever attempted, and it's debatable whether people he gave his findings to would have been able to follow the equations he laid out in all instances. It was nevertheless enough for it to be made clear to people at the university that Newton was a mathematician of unusual skill and that he had made breakthroughs during the plague year. He was, therefore, made the Lucasian Professor of Mathematics in 1669, a chair which had only been founded in 1663 through a bequest made by Henry Lucas shortly before his death. Lucas was a parliamentarian who had represented Cambridge during the English Civil Wars of the 1640s. Newton would hold the Lucasian Professorship for 33 years, though his final years were absentee as he moved to London in the mid-1690s. The position was hardly onerous. Newton was expected to deliver one lecture every week during one term of the year. For this, he was paid an income of £100 per year. Moreover, the lectures barely had any audience. Such was the lack of interest in mathematics and physics at Cambridge in the late 17th century. Even this light load was dispensed with by 1687, after which time Newton had no teaching responsibilities. What these lectures did do was allow Newton space to refine his findings from the mid-1660s and make them more accessible to an audience. To demonstrate his findings to the few students who attended his lectures, he began developing instruments to showcase his findings, notably a telescope and prism rings that showed his theories on optics. Very slowly his findings began to reach a wider audience. By 1671, the Royal Society in London had heard about his discoveries and invited Newton to send them information about his work. He was duly elected as a Fellow of the Society in January 1672. In the years that followed, his entry into the Royal Society would mean that his research findings began to spread beyond Cambridge to the wider academic community in England and then to the continent, as many members of the Royal Society corresponded extensively with natural philosophers and scholars on the continent. In an age before academic peer review journals, this was how new research was disseminated. As this happened, Newton refrained from publishing much of his work. His paper on analysis by infinite series was distributed and was eventually published in print in 1711, while another couple of works appeared as well, but Newton would ultimately wait over 20 years between when he made his breakthroughs at Woolsthorpe and when he published them in complete form. As Newton emerged in the 1660s and 1670s as one of the leading scholars of his day, he seemed to have no concurrent interest in starting a family or marrying. It was taken for granted in the 17th century that a man of his social status would marry, have children, and try to move up the social ladder. He would never do this and does not appear to have ever contemplated doing so. In fact, he seemed to have no interest in the opposite sex. This has understandably led to people questioning his sexuality. There is no evidence to suggest that Newton was gay. Instead, he just appears to have been largely asexual, with no interest of any kind in a sexual relationship. Historians were surprised to learn years ago about his possible fling as a teenager with the stepdaughter of Mr. Clark, with whom he lodged in Grantham when he was attending the grammar school there in the mid-1650s, simply because it was so unusual. The conclusion we can draw from this is that he was heterosexual, but with very little interest in women. Over time, he abandoned any thoughts of marriage and a family, if he ever gave it much consideration at all. Instead, he committed himself fully to his research and writing. This included friendships. Newton was a reclusive individual who didn't socialize much at Cambridge. When he visited London in August 1674, he made no effort to meet any of the people at the Royal Society he had been in contact with for several years by then. Instead, he went back to Cambridge a week later and continued writing to them about his work. As he aged, he did become slightly more sociable. His religious views were also unorthodox. Newton was a Protestant, as were the majority of English people by the second half of the 17th century. He was a nonconformist, though, someone who disagreed with the established views of the Anglican Church of England. In Newton's case, his nonconformity was on the extreme end of the spectrum. He did not believe in the sanctity of the Trinity of God, Jesus, and the Holy Spirit. However, he kept his religious views largely to himself. It has only been possible to reconstruct them through analysis of his notebooks. Newton's aloof and often difficult personality could translate into rivalries and conflicts with fellow scientists as the years went by. There were occasions when this was the simple over and back between scholars with competing theories. This was the case with Newton and Christiaan Huygens. Huygens was a leading Dutch mathematician, natural philosopher, and astronomer whose work also focused on optics. For instance, while Newton was still a child, Huygens had discovered Titan, the largest of Saturn's moons, in 1655. He was a scholar of considerable renown around Europe when Newton was unheard of. Both men developed competing theories about the nature of light. Huygens disagreed with Newton's corpuscular theory of light and instead proposed that light travelled as waves that then produced secondary waves or wavelets. A considerable academic debate played out between Newton and Huygens over many years about this. More toxic was the rivalry that developed between Newton and Robert Hooke. Hooke was 7 years older and was also a natural philosopher, mathematician and astronomer. He dabbled in surveying and engineering too, and had overseen a lot of the work which went into rebuilding London after the Great Fire of 1666. Hooke was working on telescopes, optics and gravity in the 1660s and 1670s, and viewed Newton's emergence as a threat to his eminence within England's scholarly community. An unpleasant rivalry developed, one which lasted decades and which famously is believed to have ended with Newton having all portraits of Hooke held by the Royal Society destroyed after his rival's death in 1703. Rivalries aside, Newton had something in common with many of these other English natural philosophers. They were all generally interested in alchemy, esoteric thought, and what was known in early modern Europe as Hermeticism. Newton's interest in these pursuits was lifelong. Alchemy is a field in which individuals sought to discover the fabled philosopher's stone, a legendary substance which alchemists believed could turn anything into gold. It was closely allied to a belief in magic and elements of esoteric or hidden history and arcane knowledge. Hermeticism was a branch of alchemical studies. The word comes from a set of teaching which were believed to have been written by a mysterious figure from late antiquity known as Hermes Trismegistus. He was understood to have been a philosopher and a proto-scientist who dabbled in alchemy. In reality, the works which early modern Europeans ascribed to him were largely derived from a mix of Neoplatonic philosophy by 3rd century AD writers like Plotinus and science as it had been carried out in the Roman Empire in the 3rd and 4th centuries AD, while elements of ancient Egyptian law and other writings were also incorporated into Hermetic and alchemical thought in early modern Europe. As such, Hermeticism was a kind of pseudo-religion and experimentation with arcane knowledge. It was very closely connected to the scientific revolution, and Newton and Leibniz were far from the only major scientists of the era who dabbled in alchemy and Hermeticism. So too did figures like Nicolaus Copernicus, Tycho Brahe, Johannes Kepler, Galileo, Walter Raleigh, Francis Bacon, Robert Boyle, and many others. The scientific revolution was deeply connected to the quest for the philosopher's stone, alchemical studies more broadly, and Hermetic thought. Chemistry, in particular, emerged as a discipline directly from alchemical studies. Thus, a visitor to Newton's study over many years would have seen scientific instruments that were designed to test the suitability of substances as the philosopher's stone, while his papers are peppered with manuscripts about alchemy and Hermeticism. As early as the 1660s, Newton's interest in the burgeoning field of chemistry was leading to him conducting research in the field of alchemy as well. He had obtained a 6-volume work entitled Theatrum Chemicum, which was published back in 1602 and which contained extensive treatises on how to carry out alchemical experiments. Newton closely read this and other works on the subject, even as he was carrying out his groundbreaking work on physics and mathematics. By 1670, his alchemical studies were advanced enough that he composed a treatise of his own entitled The Vegetation of Metals. Vegetation meaning transformation in this case. By that time, he was considering moving away entirely from natural philosophy or physics to focus on alchemy. He entered into correspondence with the leading chemist of the age, Robert Boyle, and continued to develop his laboratory at Cambridge, carrying out new experiments and acquiring all sorts of substances and equipment with which to study them. This led to the creation of an index chemicus, or chemical index, in which he noted his experiments with hundreds of different substances to find the philosopher's stone. Newton would eventually develop files over thousands of pages of notes as part of his studies in alchemy. Unfortunately, much of this was in the form of symbols, which he clearly was able to understand himself, yet which are now impenetrable to the modern reader. It does add to the sense that he was engaged in arcane research, though. In fact, he probably gave over more of his time to this than the study of physics. This interest of Newton's in alchemy and Hermeticism extended into what we would call esoteric history and thought today. Esoteric means mysterious or hidden. An example of Newton's interests in this area was the myth of Atlantis that had been described at length by Plato in two of his dialogues, the Timaeus and the Critias. Newton incorporated discussion of the fabled utopia into a long book, which he wrote entitled The Chronology of Ancient Kingdoms Amended. This explored the chronology of ancient societies, like those of ancient Egypt and Greece, the Babylonians, the Assyrians and the Persians and so forth from antiquity. It must be remembered that when Newton was writing about these, the modern disciplines of Egyptology, Orientalism and archaeology had yet to emerge, and the history of ancient Egypt and Mesopotamia was still shrouded in mystery. Some of his work was historically based. Other parts of it involved an eclectic blend of history and myth. It fed into his interest as well in the Old Testament and more obscure elements of Christian theology. For instance, Newton was fascinated by the Book of Daniel, an apocalyptic text of the Old Testament in which the end of days was discussed. Worryingly, this research into apocalyptic texts would eventually lead Newton to calculate that the world could end in either 2034 or 2060. We might not have long left. This interest in the more obscure historicity of the Old Testament saw Newton also writing in his extensive notes about the Temple of Solomon, the first Temple of Jerusalem in the Holy City, and whether it had in fact been built by King Solomon. Newton concluded that these ancient buildings and the religions around them were evidence of long-lost knowledge systems of the ancients, which alchemical studies formed just one prong of efforts to recover. In the end, Newton did not decide to abandon his work as a natural philosopher to become an alchemist, a transition which, to put it in modern terms, would have seen him switching from studying physics to chemistry. Instead, he continued to focus on natural philosophy, moonlighting in alchemy. We are fortunate that he did, for in the 1680s he began working on condensing his research and findings into one of the most important books ever written in the history of science. This was entitled the Philosophiae Naturalis Principia Mathematica, meaning the mathematical principles of natural philosophy. Finished in 1686 and then published in 1687, it contains a synthesis of all the work which Newton had undertaken since his student days at Cambridge. While he had disseminated quite a lot of this since the mid-1660s, in the form of papers and through extensive correspondence, this was a much more refined account of his findings in the sphere of gravitational laws, mechanics, and mathematics. It added greatly to European scientific knowledge. For instance, while Galileo and Kepler had observed and described planetary motions nearly a century earlier, Newton was now able to provide a scientific and mathematical explanation for why the planets moved in the way they did. It also added to knowledge about the equinoxes and the world's ocean tides. Newton even theorized about how the theory of gravity, which he had proposed over 20 years earlier, could account for physical phenomena like observations of irregular motions in the moon. It would soon come to be regarded as the most important book written during the scientific revolution. The Principia Mathematica was broken down into 3 books. The first book, entitled De Motu Corporum, or On the Motion of Bodies, provided a detailed description of his theories around gravity and the laws of motion, as well as exploring the ideas of gravitational pull, force and equal reactions that he had discovered at Woolsthorpe all the way back in 1666. This included additional discussion of the work of earlier scientists like Johannes Kepler and how bodies moved owing to things like centripetal force. These theories were then expanded upon in Book 2. Here, he was responding directly to arguments that had been made by René Descartes and others on the continent in decades gone by, and systematically showing where they had gone wrong in their analyses. Finally, in Book 3, subtitled as De Mundi Systemate, or On the System of the World, Newton attempted to demonstrate what the real-world implications of the theories he had described in the first 2 books were. For instance, there was a lot of discussion in Book 3 of how the laws of gravity and force, which he had detailed in Book 1 and Book 2, impacted on the planets and the solar system. In the course of this, Newton also laid out his own views on the nature of the solar system and the heliocentric universe. In this way, the Principia Mathematica was not just laying out new theories. It was discussing the vast range of material which constituted the scientific revolution, going all the way back to Copernicus's discoveries about the solar system and the Earth revolving around the Sun a century and a half earlier. If there is one thing that takes a small shine off Newton's accomplishments, is that many of the same conclusions were arrived at completely independently at the exact same time, hundreds of kilometers away in Germany. Gottfried Wilhelm Leibniz was born in 1646 in the city of Leipzig in Saxony in eastern Germany, a few years after Newton's birth in England. He attended numerous universities in the 1660s and then embarked on a career of exceptional scholarship. Like Newton, Leibniz was a polymath who cannot be easily categorized as a mathematician, a physicist, or a philosopher. He worked in an extensive range of fields and, as Newton increasingly would as his life went on, he also worked for the government and performed a range of administrative and bureaucratic roles, even working for Peter the Great, Tsar of Russia, to modernize the Russian state in the early 18th century. Leibniz's research led him to make many of the same discoveries that Newton was making in England between the 1660s and 1690s. In particular, both men made the same breakthroughs in developing the field of calculus, though Leibniz was more practical in his application and even invented the Leibniz wheel as a kind of basic mechanical calculator. So similar were the discoveries that the two men made completely independent of one another that later in their lives an academic argument broke out in which they both claimed to have been the first to make their discoveries. In the course of this, Newton disingenuously used some letters he had written to and from Leibniz back in the 1670s to try and claim his German counterpart had copied his findings. If nothing else, what this demonstrates is that societies have to arrive at a certain threshold of knowledge in a given discipline before individuals can make specific breakthroughs. Both men reached the same conclusions at the same time because they were building on the work of Galileo, Kepler, and others. Similar phenomena are seen in other time periods. Over a century and a half later, both Charles Darwin and Alfred Russel Wallace would arrive at almost identical ideas about evolution and the survival of species independent of one another, yet at the same time. Newton published the Principia and Mathematica just as England was entering into a period of pronounced political instability. 2 years earlier, in 1685, King Charles II had died. Although he had fathered a huge number of illegitimate children with over half a dozen different mistresses, his marriage to his Portuguese wife, Queen Catherine of Braganza, had been childless. Without a direct, legitimate heir, the throne passed to his brother, James, Duke of York. The problem was that the newly ascended King James II was a Roman Catholic at a time when anti-Catholic sentiments in England and Scotland were running very high. An already unstable political dynamic boiled over when a son was born to James in the summer of 1688, one who would now be raised as a Roman Catholic, putting in place the possibility of an extended return back to Catholicism in England. James did nothing to alleviate these concerns and unwisely began placing Catholics in positions of power in England and Ireland. Within weeks, a powerful alliance of English aristocrats and politicians had written to James's son-in-law, William of Orange, the most powerful figure of the Dutch Republic and the husband of James's daughter Mary. They offered him the throne, and William duly headed to England with an army to enforce his claim. By the time the year 1688 was out, James had fled to France, and William and Mary were about to become joint rulers as King William III and Queen Mary II. The Glorious Revolution was a period of instability, and it continued into the 1690s as war followed between England and the Dutch Republic against the French, who were backing James's claim to be restored to his throne. These events had a bearing on Newton's career. His aloof character meant that he had always avoided becoming involved in Cambridge's politics. However, early in 1687, while he was still king, James II had attempted to take over the university politically by installing Roman Catholics like the Benedictine monk Alban Francis as members of the Senate that ran the institution. This annoyed Newton, a religious nonconformist who viewed even Protestant Anglicans poorly and who perceived Catholics as adherents of a branch of Christianity which had little or no basis in Scripture. He therefore became involved in the internal wrangling at Cambridge to try to maintain the political and religious independence of the university. In 1688, this led to Isaac and 7 others being ordered to come to London to answer for their efforts to resist James's attempts to enforce control over Cambridge. This brief foray into political activity was enough that when the Glorious Revolution had occurred, and a new Convention Parliament was being assembled early in 1689 to ratify the political changes, Newton stood for election at Cambridge. He won a seat and headed for Westminster. His contributions were limited. Newton backed the constitutional changes which saw William and Mary become king and queen on the basis that Parliament's power relative to the monarchy was vastly increased in England. But He never spoke before the Parliament. A legend has it that the only vocal contribution he made to the Convention Parliament was to ask an usher to close a window that was creating a draught. Despite this, he was elected again as a member of Cambridge University in 1701, though a third election attempt in 1705 was unsuccessful. More broadly, Newton's brief forays into politics were important in that he spent more time in London and his social circle expanded slightly. In particular, he developed a friendship with the noted philosopher John Locke, whose areas of focus were optics and epistemology, the theory or study of knowledge. Life in London saw him become a government employee. In 1695, he was one of 8 individuals that the government contacted about the issue of English coinage being clipped. By the late 17th century, money was still circulating exclusively as coins made out of metals like silver and copper. Notes were starting to appear as instruments of exchange within the business community, but it was a long time before they would become part of day-to-day economic life. The issue with the coinage in the 1690s was that the stresses of war with France following the Glorious Revolution had led to people clipping the nation's coins. This is where a small sliver of silver was clipped or cut off the edges of coins. If this was done with a large amount of coins, a person could get themselves a nice haul of silver. Clipping was reaching epidemic proportions by the mid-1690s, and Newton was one of the individuals contacted about coming up with a solution. This first engagement with the government led to him being offered the post of Master of the Mint a year later in 1696. Over the next 2.5 years, he oversaw a complete recoinage. This was where an early modern government called in all of the old coins, melted them down, and minted new ones that were reissued. The new coins were issued with features which made it obvious if they had been clipped. Nearly £7 million worth of coins were minted and issued between the spring of 1696, when he became Master of the Mint, and the end of 1698, roughly the same amount as was usually issued over 30 years. The accomplishment points towards Newton's considerable abilities as an administrator, though his coins were undervalued by comparison with European silver, and England's new silver coins soon started vanishing to France, where people could exchange them for higher amounts of money. Despite his position as the leading natural philosopher of his age in England, Newton had only played a limited role in the activities of the Royal Society for much of his life. This was broadly owing to his acrimonious relationship with Robert Hooke. Hooke had a lot of supporters within the society, and Newton had been marginalised within it as a result. However, Hooke died on the 3rd of March 1703, paving the way for Newton's rapid ascent. Many members of the organisation felt it was in need of a more scientific-minded leader after years in which 2 nobles, Charles Montague, 1st Earl of Halifax, and John Somers, 1st Baron Somers, had held the position of president. In this vein, at a meeting of the Society's members in November 1703, Newton was elected as the new president. He would hold the position down to his death, becoming the second longest-serving president ever, eclipsed only by Sir Joseph Banks, who held the office for a huge period of over 41 years between 1778 and 1820. 2 years after he became president of the Royal Society, Newton was also knighted, becoming the first scientist or natural philosopher ever to be awarded such a title in Europe. As president of the Royal Society, one of Newton's foremost achievements was balancing the Society's books. It was badly in debt in 1703. By 1710, he had not only managed to remedy its financial situation, but had also enough of a surplus to acquire a new property at Crane Court, near Fleet Street in London, which became the Royal Society's home in London for many years. Other actions were less admirable. He developed a rivalry with John Flamsteed, the head of the Royal Greenwich Observatory, resulting in Newton trying to suppress Flamsteed's work and steal his research. The whole episode highlights the more unsavoury elements of Newton's personality. While Newton's dual roles as Master of the Mint and President of the Royal Society kept him busy with government duties of one kind or another from the mid-1690s onwards, he did find time to continue his scholarly research and publishing. In 1704, he published Optics, or a treatise on the reflections, refractions, inflections, and colours of light. In this, he expanded on his earlier work in the nature of light and how humans observed light refraction through glass and other substances. This was a synthesis of things Newton had written and lectured about since the 1660s. For instance, it contained one of the first detailed discussions of how light, when filtered through a glass prism, separates into different colours, the same thing which is witnessed in rainbows. This involved a fundamental revision of Western ideas about the nature of light. Going all the way back to studies conducted by Aristotle in ancient Greece, it had been assumed that light was one single colour. Newton made it clear that this was not the case. The book also expanded on the idea of historical method and research. His decision to publish the first edition of the book in English, rather than in Latin, was also important, signalling a shift away from the medieval and Renaissance notion that Latin was the unquestioned language of scholarship. Newton also spent a lot of time working on an expanded and revised second edition of the Principia Mathematica, published in 1713. As his efforts to suppress John Flamsteed's work and plagiarize his research indicates, Newton was also quite interested in astronomy and study of the stars in his later years. In this, he collaborated with Edmund Halley, the English astronomer who Halley's comet is named after. Halley used Newton's gravitational laws to calculate how often the comet would be visible from Earth, coming to the conclusion that it would be seen approximately every 75 years. Newton turned 70 years old at the very end of 1712. This was quite old by the standards of the 18th century, and his thoughts were now turning to his legacy rather than any sort of groundbreaking new work. Over the next decade and more, he published several new editions of his works, notably a French edition of Optics, which made his research and findings more widely available on the continent. He entered into numerous arguments with other scholars on the continent about who had developed particular theories first. Newton was also employed by the government on a number of different scientific projects. One involved efforts to find a way of measuring longitude while at sea. The British Royal Navy had emerged as the finest navy in the world, and as Britain's colonial and imperial expansion accelerated, the government wanted to find better and better ways to explore the uncharted parts of the world. Newton spent time in his later years reading papers that discussed various theoretical ways of measuring longitude, but a fully functioning marine chronometer would not be successfully developed until John Harrison in 1761. Beyond this, Newton spent a lot of his later life returning to the study of esoteric subjects and theology which had held his interest throughout his life. His research on prophecies and apocalyptic religious thought were eventually published after his death as Observations upon the Prophecies of Daniel in 1733. In this, he had pondered the possible end of the world as his own life was also winding down. His health deteriorated from 1722 as he entered his 80s, though he continued to work. On the 2nd of March 1727, at 84 years of age, he chaired a meeting of the Royal Society. Afterwards, he became ill and his health deteriorated quickly. Newton died on the 20th of March 1727, the 31st of March on the continent. He was laid to rest in Westminster Abbey after a funeral attended by the leading figures of his age. Newton had been remarkably reticent about publishing his research during his lifetime. More than 20 years elapsed between his period of great discovery in 1665 and 1666 and when he finally published his work fully in the Principia Mathematica in 1687. This was mirrored in the amount of work which was left unpublished at the time of his death. Therefore, nearly more of his research was published posthumously than had been so during his lifetime. In 1728, just a year after he died, a collection of his lectures and writings on optics from Cambridge was published. That same year, his Chronology of Ancient Kingdoms amended, his work of history and theology that he had worked on over many years, appeared in print. 5 years later, his apocalyptic text of Observations on Daniel and the Apocalypse of St. John was also published. In 1754, the text of his correspondence with John Locke on scriptural matters was published as An Historical Account of Two Notable Corruptions of Scripture. As such, a lot of Newton's esoteric and theological work was published not long after he died. In many ways, though, the most consequential of all of Newton's written output are his extensive notebooks, correspondence and working papers, huge amounts of which have survived. His notebooks are generally found in the libraries of Cambridge University, though one of his earliest notebooks, dating all the way back to 1659, is today housed in the Morgan Library in New York. Extensive correspondence is extant by him, generally at Cambridge for the period of his life, prior to moving to London in the mid-1690s, and then in the National Archives of the UK in London for the years after he moved to the capital. With extensive digitisation and transcription, Newton's entire research career and virtually everything he wrote is available for the whole world to consult online today. Newton was already regarded as one of the geniuses of European scholarship and science in his own lifetime. His reputation in the 18th and 19th centuries was similar to that of Albert Einstein in the modern world. And yet, just like Einstein, Newton's work has been re-evaluated over time and revised. For instance, his work on gravity did not take account of how gravitational pull occurs beyond Earth itself and how it is impacted by things like black holes. There was simply no way for him to even begin measuring this in the 17th century. In this sense, it could be said that Newton's law of gravity was incorrect, but this misses the point. It was a stepping stone towards a more perfect understanding of how gravity functions. Science is a journey rather than a destination. The same thing has happened with Einstein's theory of general relativity. While it might have transformed the field of physics at the start of the 20th century, it is now appreciated that there are several theoretical shortcomings within it. But, like Newton before him, Einstein didn't have the benefit of the kind of technology available to modern physicists like quantum computing and the Large Hadron Collider at CERN in Switzerland. The re-evaluation of the transformative work of figures like Newton and Einstein is a normal process in the evolution of knowledge. Each generation builds on the last and eventually reaches a new threshold of knowledge based on earlier findings and new ones. There is no denying Newton's influence, though, on all those who came after him. The great theoretical physicist, Stephen Hawking, called the Principia Mathematica the most important book ever written on the hard sciences. Many would still agree 3 centuries after Newton's own time. Isaac Newton was undoubtedly one of the greatest figures of the scientific revolution. The peculiar thing about this is that his background would not have suggested his emergence as a great scientist or natural philosopher, as it was known in the parlance of the time. Newton hailed from rural England and came from a difficult family background, complicated by the death of his father before he was even born. There was no tradition of scholarship in his family. Indeed, his father and several other family members were illiterate. This being said, his family background possibly drove him to intellectual pursuits. Ensconced in a dynamic where he was marginalized by his mother's second marriage, he applied himself to his studies. A number of early influences, like his teacher at the grammar school in Grantham when he was young, Mr. Stokes, imparted the basics of mathematical inquiry to Newton. Then he went to Cambridge. He never applied himself in a dedicated manner to the standard curriculum. Instead, Newton began his own investigations into physics, mathematics, and optics based on his reading of thinkers like Galileo and Kepler, whose works were still revolutionary in the 17th century. Based on these and his own penetrating mind, he developed some of the most important concepts about how gravity functioned, as well as calculus and optics, all while he was still in his early 20s. 2 decades later, in 1687, he published one of the most important books ever written in the history of science, the Principia Mathematica. His story also points towards the unusual nature of the scientific revolution and the way that science and government overlapped to a greater extent in the 17th and 18th centuries than they do today. Newton, for instance, pursued studies in alchemy and esoteric knowledge, like all of his contemporaries in the field of natural philosophy. Later in life, he was drawn into government service and became Master of the Royal Mint in England. Throughout his life, he remained a difficult individual who few people knew much about on any personal level. In short, he was both complicated and brilliant. What do you think of Isaac Newton? Was he one of the most radical thinkers in the history of Western thought, or does the fact that Leibniz made many of the same discoveries as he did, independently of him, detract somewhat from the significance of Newton's work? Please let us know in the comments section. And in the meantime, thank you very much for watching. Newton and his fellow natural philosophers transformed European understanding of science in the 17th century. At the start of that 100-year period, his predecessors, like Galileo, were striving just to convince people of the merits of heliocentrism, the idea that the Earth revolved around the Sun and not the other way round. By the dawn of the 18th century, Newton and his colleagues were increasingly revered, and the desire to understand the dynamics of the physical world was swelling. Contradictions always existed, though. Newton was an alchemist as much as a scientist, and many of the greatest minds of the scientific revolution and the Enlightenment that followed it continued to believe in some fairly superstitious or even ignorant things. That was even truer of other disciplines like biology and medicine. These were only transformed in the 19th century. It was not until the days of Charles Darwin and others like him, between the 1830s and 1870s, that human understanding of evolution, human biology, and how species evolve began to change. The cognitive leap was dramatic. Throughout history, writers have been devising elaborate religious and mythological claims to explain where human beings had come from and how they had suddenly manifested in the world through divine intervention. Darwin offered a new explanation. Human beings hadn't been created. They had evolved from something dramatically different, often by responding to the specific dynamics of the environments they lived in. And this process likely took hundreds of thousands of years. Darwin's discoveries all started 2 days after Christmas 1831, when, as a 22-year-old naturalist, he boarded the HMS Beagle as it prepared to commence a voyage around the world that would last for nearly 5 years.
The man known to history as Charles Darwin was born on the 12th of February 1809 in Shrewsbury, the county town of Shropshire in the west of England. His father was Robert Waring Darwin, a physician who was remembered in part for his towering stature and imposing frame, at over 6 feet in height and weighing 24 stone. Darwin later recalled that his father was the largest man he had ever seen, and noted the conversations that he would have with his father, who assumed that his son would follow him into the medical profession. Charles Darwin's mother was Susanna Darwin, née Wedgwood, who died suddenly when Charles was aged 8, of either a severe ulcer or stomach cancer. He later recalled that he could remember hardly anything about her except her deathbed, her black velvet gown, and her curiously constructed work table. Charles's grandfather on his father's side was Erasmus Darwin, a noted scientist who had mooted a theory of evolution in his poem The Loves of the Plants, written in 1789, in which he referenced vestigial organs in plants, flies, and humans, noting, for instance, the fact that human males had nipples, and flies' unused fourth wings. He also created designs for a rocket engine which would be powered by hydrogen and oxygen, a canal bridge which would lift barges, and a copying machine, many of which were not realized in practice until long after his death. Erasmus Darwin was a notable writer and an accomplished man of science who turned down an offer from George III to become his royal physician, and instead directed his attention to the writing of poetry and the management of a new club, the Lunar Society of Birmingham, which was devoted to philosophical discussion between industrialists, scientists, and poets, to name a few. The relationship between Erasmus and his son Robert was strained, leading Charles to have little contact with his grandfather's theories and writings. These were not treasured by Robert, who instead attempted to encourage the young Charles to become a man of medicine. The Darwin family also included several other children, including one younger and 3 older sisters, as well as a single brother, Erasmus, who was 5 years older than Charles. His sister, Caroline, provided Charles with his first education, despite being only 9 years older than him. Having been educated for a time by Caroline, Charles later became a student of the Reverend G. Case, a Unitarian minister who noted that Charles had a passion for collecting various ephemera from the natural world, including seashells, minerals, and stones. When aged 9, Charles was enrolled at Dr. Butler's school in Shrewsbury, where he boarded, despite only living a mile away. He recalled later that he would often run home before the school was closed for the night in order to see his family, which, he argued, was absolutely essential in maintaining his mental health and well-being. Darwin spent much of his free time reading and was deeply interested in the poetic works of Byron and the writings of Shakespeare, although he later lost interest in them. He was also fascinated by the idea of travel and enjoyed reading works which depicted adventure and foreign lands. Charles's interest in science stemmed both from his readings and from the activities of family members. His brother's interest in chemistry led him to construct a makeshift lab in their garden shed, and his uncle excitedly instructed Charles on the operation of a barometer. His fascination with fauna was augmented on family trips, such as those which the Darwins made to the Welsh coast, in which Charles noted that the insects and flowers to be found there were not always the same as in his home county. Charles performed with average success at school and entered the University of Edinburgh when he was aged 16, although it was noted by his father that a significant reason for his leaving school early was because he lacked any great progress in his studies there. Charles was emotionally healthy, from what we can gather from contemporary reports and autobiographical statements, although he recalled that he had once kicked his puppy for the sense of power that it afforded him, and that he was sometimes frustrated by the social standing of the sciences, which were often regarded as beneath a gentleman. Entrance to the University of Edinburgh was encouraged by Charles's father on the basis that this would lead to his inevitable medical career. The university was a renowned centre for medical learning and counted amongst its alumni Charles Bell, the discoverer of Bell's palsy, as well as the functions of the root of spinal nerves, William Hewson, the father of hematology, and James Lind, who discovered cures for scurvy and typhus, as well as the model for the first clinical trial. Charles entered the university with some misgivings about his own enthusiasm for the course, and was not helped by the poor teaching standards he found there, later recalling the boredom he had felt in lectures, and bemoaning the lack of hands-on experience which his teachers afforded him and his classmates. University had nonetheless given Charles some experience which he would later come to rely upon. He presented his first academic paper to the Plinian Society while studying there, and had met an academic who would later come to support his theory of evolution, one Dr. Grant. After 2 years at Edinburgh, Charles had decided that he no longer wished to study medicine, following in the footsteps of his brother who had already quit his medical course at Edinburgh, and his father decided instead that he should enter the clergy as an alternative. Charles was entered at Christ's College at the University of Cambridge when aged 19. He once again, by his own admission, wasted his student days by becoming involved with a group of fellow students who preferred the shooting field to the library, and he gained a pass mark in his final exams. The university had been invaluable to Charles as a means of introducing him to academics who would be formative in his own pursuit of science. J.S. Henslow and Adam Sedgwick both influenced Charles as a student and later in his life. Henslow was the man who would arrange Charles's journey on the Beagle and often met with him for walks and discussions about science and art. Darwin also befriended H. Thompson, later an MP, and Dr. William Whewell, who was to become the Master of Trinity College and later the Dean of Hereford. Darwin left Christ's College in 1831 and joined Sedgwick on an excursion the same year to North Wales, where he was taught the theory and method of geology and was given an opportunity to apply his newfound skills as part of an academic investigation. In August 1831, Henslow wrote to Darwin and informed him of an expedition planned aboard the Beagle, a Cherokee-class 10-gun brig sloop of the Royal Navy, Her captain, Robert Fitzroy, had written to Henslow and had stated that he would welcome a naturalist on his voyage, given that they would undertake the journey without pay. Darwin was delighted at the chance to undertake a voyage as a naturalist aboard a Royal Navy vessel, although his father was angered that he was yet again stepping further from a career as a doctor or a clergyman. Charles implored his uncle to speak to his father, and after a discussion between Josiah Wedgwood and his brother-in-law, Robert agreed to let Charles embark on the Beagle. On the 27th of December 1831, the HMS Beagle departed from Devonport. Charles, with a degree in theology and classics, was her resident naturalist. Scientifically, he was alone and had no one of comparable experience or expertise, even though he lacked an academic background in the discipline which underpinned his vocation. Charles spent his first day aboard the Beagle constructing a timetable for himself, which would allow him to become acquainted more intimately with the subjects of meteorology, mathematics, and biology, as well as other subjects such as French and the Greek New Testament, which he decided would form the basis of his reading on Sundays. He also had copies of Paradise Lost and Humboldt's Personal Narrative, in which the scientist and explorer Alexander von Humboldt detailed his adventures to the Americas. Darwin noted in letters home that he had a difficult relationship with the captain, Fitzroy, as did many other members of the crew. Fitzroy was a member of the aristocracy and an illegitimate descendant of Charles II, with a wicked temper which would flare erratically. Darwin also recounted an event in which he argued with Fitzroy on the subject of slavery, which the latter supported. Darwin wrote that the argument had been so fierce that he had pondered leaving the Beagle altogether. Darwin shared his lodgings aboard the Beagle with Augustus Earle, a draftsman, and became friendly with several other members of the crew, including John Stokes and Charles Musters, a first-class volunteer. Another, Sims Covington, was a cabin boy who was later to become a personal assistant to Darwin. Over the course of the voyage, Darwin's notes show a man becoming ever more convinced of the potency of natural selection, as well as his conviction that fossils were the remnants of life forms which had existed before humans had appeared, all of which he formulated during his first few weeks at sea, as he studied aboard the vessel in his cabin. He concurrently battled seasickness and wrote simply that the Bay of Biscay was hell. During the first weeks of 1832, Darwin commenced practical studies and developed a net for collecting plankton, which he studied and wrote about emphatically in his diaries, noting the vast array of colors and forms which these creatures took. On the 16th of January, the Beagle made landfall on St. Jago in the Cape Verde Islands off the coast of modern-day Mauritania. He recalled that upon setting foot on the island, he was entranced by the volcanic rocks, the song of strange birds, and the vast array of flora and fauna that he saw. During his time in the Cape Verde Islands, Darwin developed a theory that hard white rocks, which littered the islands, were formerly molten lava flows which had flown over the seabed and contained imprints from shells and coral reefs. On the 28th of February, the crew of the Beagle alighted on the shores of Bahia, now a state of Brazil, and home to the city of Salvador. He wrote that this land is a chaos of delight, and his time in Brazil was to have a great impact on him and his work. He wrote of the beauty of the wildlife and of the nature in Brazil, and argued that this was nature in its grandest form. He also stated that, to a naturalist, there was a pleasant nuisance in having to stop every few yards to study a new creature or flower. Darwin also encountered much slavery in Brazil, which was the last country in the Western world to abolish the practice, which it eventually did in 1888. He was deeply disturbed by what he saw, and wrote that, "I hope the day will come when they will assert their own rights and forget to avenge their wrongs." Darwin and his companions settled at the small village of Botafogo, which was located a short distance outside of Rio de Janeiro, situated on a lagoon. He soon embarked on a 3-week ride into the countryside from his base, during which he travelled a distance of several hundred miles, in what would have been a dramatic and exhaustive introduction to his new landscape. When working from his base in Botafogo, Darwin also maintained a strict routine and collected specimens one day, to be followed by a day of preserving and analysing his finds on the following day, a 2-day timetable which he maintained for the duration of his stay. Darwin was able to observe dramatic and exciting natural events in person when in Brazil, and noted with great interest an incident in which he had witnessed a vampire bat bite a horse, and made notes on glowworms, butterflies and fungi. On the 5th of July 1832, the Beagle left Rio and travelled south for Montevideo, now the capital of Uruguay. Upon their arrival, the crew were informed that a revolution was taking place in the city, an event which was part of a series of conflicts which had emerged in Uruguay following the Declaration of Independence in 1828, and reflected a conflict between two political factions which had entered the vacuum which followed. The conflict into which the Beagle had strayed was a rebellion by the Montevideo garrison in support of Juan Lavalleja, the leader of the 33 Orientals, a revolutionary faction which opposed the presidency of Fructuoso Rivera, a veteran military commander who was the incumbent leader. Fitzroy made the decision not to land in Montevideo and instead proceeded to Buenos Aires, whereupon they were fired at by an Argentine naval vessel, a problem which was later rectified by the governor. After this, the Beagle returned again to Montevideo, and Fitzroy requested to land at a private mooring. After this stop, the Beagle continued south, hugging the coastline in order to observe it. It was during this stretch of the journey that Darwin was marooned for a single night. This was due to bad weather, which meant that the Beagle was unable to come and pick him up from the island, at which he had stopped in order to take samples. He would later write that he never knew such cold, although the experience allowed him to come across samples of fascinating fossils, such as that of the extinct giant armadillo and the giant sloth. The ship continued to pace back and forth between Buenos Aires and Montevideo, allowing the crew to send and receive mail, and Darwin to ship off his specimens home. Fitzroy, the captain of the Beagle, was also able to undertake a disturbing practice when he released 3 Fuegan prisoners that he had attempted to westernize from a previous voyage, sending them back to their communities with a bizarre assortment of items, such as cabbages, tea trays, cutlery, and wine glasses. This was an incident, however, which Darwin expressed his opposition to. The next few weeks were spent by Darwin undertaking riding expeditions around Buenos Aires and Patagonia, during which he reported to have felt the extremes of human comfort, writing that he often suffered from a great thirst and that the seemingly endless riding had caused him to feel incredibly tired. He was also plagued by mosquitoes and reported that the jaguars which inhabited the surrounding forests had caused great fear amongst his guides. On returning from an expedition back to Buenos Aires, Darwin found himself unable to enter the city on account of another revolution, and instead was forced to remain outside the city proper for a great period of time. He was unable to reach the Beagle until the 4th of November, after which the vessel sailed, eventually calling into the Rio de Santa Cruz in Argentina. The Beagle had been damaged over the course of her voyage and required repairs, which were undertaken at the mouth of the river. Meanwhile, Fitzroy had planned an expedition to the Cordillera de la Costa mountain range, which would require the crew to embark on a 245-mile trip upstream, a journey which was spread over 13 days, and which the captain ultimately deemed a failure. On the 12th of May 1834, the Beagle set out on her final trip south and crossed into the Pacific Ocean on the 9th of June, eventually reaching Valparaiso in Chile at the end of July. From here, Darwin trekked the Andes and was able to observe the differences in flora and fauna which correlated with their altitude. Darwin then contracted an illness, likely to be Chagas disease, which caused him to experience fever, swollen lymph nodes, and headaches, and to which some historians attributed his later poor health, such as his lethargy and heart problems. He reported at the time in his letters home that he had experienced great periods of tiredness and that he had suffered from blackouts and confusion. From Valparaiso, Darwin made one of his most important geological expeditions and ascended 10,000 feet into the Andes in order to observe the segmentation of the Earth from the sides of the mountains which surrounded him. He commented that it was the first view I ever saw which really resembled those pretty sections which geologists make of the inside of the Earth. Darwin also advanced on one of his longest expeditions, traveling some 450 miles to the north, during which he collected well over 100 geological specimens, which he labeled and recorded. By this time, he had been away from home for over 3.5 years, and his letters, despite showing his excitement at his work, reflected an ardent desire to return to England. On the 7th of September 1835, the Beagle sailed for the Galapagos Islands, which were to become synonymous with Darwin's work. As soon as the ship anchored off the islands, the focus of Darwin's work switched from geology to biology, and he noted eagerly that the flora and fauna of the islands closely reflected those of South America. Darwin's observation of tortoises and birds on the islands stemmed from his interest in the fact that locals were able to identify which island an animal came from on the basis of their appearance. Such was the localization of their variants. He realized that finches on the various islands had differences in their appearance, which correlated with the island from which they had originated. The beaks of the Galapagos finches were of particular interest to Darwin, and he noted that some were better suited to the consumption of insects and some seeds, suggesting they were adaptations to specific environments. However, his notes at the time suggest that he did not realize the implications of his observation, writing that, "When I see these islands in sight of each other, and possessed of but a scanty stock of animals, tenanted by these birds, but slightly different in structure and filling the same place in nature, I must suspect that they are only varieties." The Beagle remained in the Galapagos archipelago for a further 4 weeks, from which it sailed south over the Pacific, spending Christmas Day of 1835 in New Zealand. While there, he commended the work that was being performed by missionaries in the region, and indeed, one of his first published reports from the voyage was included in an edition of the South African Christian Recorder, in which he wrote, "Missionaries thoroughly deserve the warmest support not only of individuals, but of the British government." Such was his interest in the work of these organizations. Darwin co-signed this statement with the Beagle's captain Fitzroy. On the 12th of January 1836, the Beagle landed in Australia in what was the 5th year of her expedition. He noted in his diary that he was pleased to have a level of immunity to European diseases. Such was the suffering of native communities with illnesses such as measles. In Australia, Darwin also noted the similarities between different species of mammal and noted their development had occurred in tandem with those of other continents. He stated in his notes that he was surprised that such similarities had developed through such a varied pathway, noting that it seemed as if two creators had come by the same product through an entirely different process. The Beagle soon set sail for home and made an unexpected stop in Bahia, where the ship had landed 4.5 years before. Darwin was exhausted and craved a return to England, writing, "We have now steered, thanks to God, a direct course for England." Darwin, on the return voyage, reflected on the majesty of the untouched natural world which he had been able to encounter through his journey, and the power of nature which he had been able to discover undefaced. This he referred to as an almost religious experience, writing that it inspired a feeling that there is more to man than the mere breadth of his body. On the 2nd of October 1836, the Beagle landed at Falmouth in Cornwall, and 2 days later, Darwin had returned to his home in Shrewsbury for the first time in over 5 years. He found that his family welcomed him home with open arms, and his father, impressed with his discoveries, accepted his choice of career as a naturalist. Once he had returned home, Darwin went to Cambridge and then to London in order to arrange and edit the official Zoology of the Voyage of the Beagle, in which he wrote extensively about the journey as well as his discoveries and ideas. Humboldt, his hero, was impressed with Darwin's work and praised his writing on travels in the tropics. Over the course of the 1840s, Darwin published further works which stemmed from research which he had conducted on the Beagle, including coral reefs, volcanic islands, and geological observations on South America, and was able to encounter various great scientists such as Sir Charles Lyell and Sir Joseph Hooker. Lyell was a prominent scientist and proponent of the theory of uniformitarianism, the idea that present-day natural laws and processes exist not just here today, but through space and time. Darwin adopted this theory and argued further that it could be used to explain a continuous process of change in organisms. Hooker was a young man and shared a great love of naturalism with Darwin. The two became firm friends, and it was to Hooker that Darwin confined his theory of natural selection, which remained a secret between the two for a number of years. By the time that he had returned from his voyage, Darwin was convinced that organisms underwent a process of change and adaptation. He further theorized that this could be the case on a grand scale, and that the change which occurred within a species could be responsible for wholesale and dramatic changes, both in their appearance as well as their mode of life. In July 1837, Darwin commenced work on a new text which he called The Transformation of Species, and only just over a year later, he had recorded what he now called the theory of natural selection. Darwin documented the thought process that led to his theory in his notebooks. He began from an observation that sexual reproduction leads to greater variation in a species than does asexual or parthenogenic reproduction. Darwin noted that, through reproduction, offspring within a species had differences from one another and from their parents, which can be referred to as random variation. These differences themselves did not appear to be directed toward any environmental advantage or design, and were random, sometimes inhibiting the capacity of the organism to live, and other times enhancing it. A variation could, over a period of time, become ubiquitous amongst a population of offspring if it provided an advantage in life. Those within a species who were better suited to a certain environment would live and pass these characteristics on to their own offspring, leading an entire population within a certain area to bear these particular variations. Much of Darwin's theory was also based on establishing a common ancestor of species which had diverged from one another in present characteristics, which he did through an examination of fossils, demonstrating that species who shared relatively few characteristics with one another had in fact stemmed from the same ancestor, and that they had diverged from one another through adapting to particular environments. Darwin noted this point in his writing, stating that in South America, parent of all armadillos might be brother to Megatherium, now dead. The level of variation in nature had been well covered in previous works. The Archdeacon William Paley, often credited with articulating an argument for the existence of God from design through an analogy involving a watch, had himself written of the great differences present amongst animals and plants, which he had presented in his work Evidence for Christianity. Darwin was puzzled by the potency of seemingly designed adaptations among species which had evidently undergone random variation. This evidently frustrated him, and he wrote later that how selection could be applied to organisms living in a state of nature remained for some time a mystery to me. It was whilst reading Thomas Robert Malthus's work on population on the 3rd of October 1837 that Darwin finally cracked the mystery of selection, explaining the preservation of useful variation and the disappearance of unhelpful or inhibiting variation. Much of the remainder of Darwin's professional life was defined from this point. He was committed to demonstrating the potency of natural selection as an explanatory theory for the modern natural world, and worked hard to document it in Nature. Darwin also had other matters on his mind in 1837. The latter part of the year saw him construct a document in which he debated the various pros and cons of getting married, in which he weighed a fear that he would be unable to travel and would have greater financial commitments to a constant companion, charms of music, and female chit-chat. He eventually erred on the side of marriage and entertained the joys which would come with it, before concluding, "Marry, marry, marry, QED." Darwin evidently also had a constant companion in mind when he wrote his list, and proposed to Emma Wedgwood soon afterwards, and on the 11th of November 1838, the two were engaged to be married. Darwin and Emma departed on a week's holiday from London, after which they moved into a townhouse at 12 Upper Gower Street on New Year's Day 1839. Indeed, 1839 started well for Darwin, and he was appointed a member of the Royal Society on the 24th of January, 5 days before his wedding. The couple remained in London for a time, although increasingly poor health had motivated them to make a change. Darwin and Emma moved to a country home named Down House in the Kentish village of Down. Hooker and T.H. Huxley, a fellow biologist, were regular guests at Down House, and Darwin wrote lovingly of the rural isolation of the place and the solace which it afforded him to conduct experiments, read, and spend time with his family and close friends. On the 27th of December 1839, William, the first of 10 Darwin children, was born. William was of great interest to his father in many ways, including scientific, and he kept a detailed record of his son and his activities, including the ways in which he developed and adapted. Darwin was, by all accounts, a loving and devoted father, who dedicated time in playing with and helping his children. He was very concerned with their health, but afforded them great freedom. Down House was a perfect environment in which Darwin could continue his research, and he stored vast amounts of information from his studies there, specimens and notes, as well as letters and documents that he had received from around the world, with information from experts and naturalists across the globe. Despite the joys of family, Down House, and his advancing scientific work, Darwin was plagued by illness from 1837 until the time that he died in 1882. When his father died, he was too ill to attend the funeral procession, and a dinner held after a scientific presentation could rob him of strength for a number of days. Darwin also suffered from a great deal of self-doubt, which he had surrounding the potency of his own theory of evolution, refusing to publish his findings until he had collected a wealth of evidence which he could use to overwhelm any potential critics. Originally intended to be a short essay, Darwin produced a draft for a 230-page-long work in which he outlined his theory and provided an incredible barrage of evidence for it. He had intended to keep the work to himself, although was encouraged by Hooker and Lyell, who were impressed and urged him to make his findings public. One of the major motives for Darwin's eventual decision to go public with his findings was the receipt of a letter from Alfred Russel Wallace, in which Wallace posited precisely the theory that Darwin had developed and asked him for a comment. Darwin did not wish to rob Wallace of what was a perfectly legitimate independent discovery, and arranged to have his findings published alongside Wallace's in a joint paper. It was this product that was presented before the Linnean Society on the 1st of July 1858 and later published in the Society Journal. After this presentation, Darwin was motivated to more fully explain his own theory and findings, and did so in the form of the Origin of Species, which he managed to complete in the remarkably short period of 13 months. He would go on to write 10 further books, all of which laid out his position and provided evidence, and in doing so, he changed mankind's perception of the natural world in a profound manner. There are several reasons why Darwin waited such a long time to formally present his findings. He was greatly concerned with ensuring that he provided a mass of evidence to back up his claims, and was sidetracked somewhat by his work with barnacles, work which led him to investigate their reproductive processes and which showed him the significant variance in the phenotypes which developed. One of the major forces that influenced Darwin to produce and publish his Origin of Species was undoubtedly the influence of Wallace, and it is important that his work be remembered alongside that of Darwin as research which revolutionized biology. Once it had been produced and published, the Origin of Species was a hit. The first edition sold out on day one, and the subsequent editions which were drafted and produced were in great demand. The book itself was thoughtful and well organized, presenting the basis of the theory of evolution alongside a wealth of evidence which covered all major areas of known biology. Darwin also tracked the evolutionary development of several organisms and investigated how organs had become specialized to their roles, how some species had become extinct, and forecasted the explosion of the human population. One of the reasons for the success of the work was the review it received from the noted zoologist Thomas Henry Huxley, who praised the work and exclaimed, "How extremely stupid not to have thought of that." Several other highly influential scientists endorsed Darwin's work, including Hooker, Lyell, and Canon Tristram, the zoologist of the Bible. However, Darwin encountered much criticism as well as praise for his work, and was roundly attacked by writers such as Philip Goss, who asserted in his book Omphalos that the world had been created by God in the way that it now appeared. In other words, that nothing had changed since the world had been created. His book fell flat. Other critics attacked Darwin on a scientific basis. Adam Sedgwick argued that he had abandoned the accepted scientific method as it had been formed under Francis Bacon, and another dangerous opponent was presented in the form of Richard Owen, an anatomist and paleontologist who attacked the Origin of Species in a lengthy review, which Darwin himself stated was malignant and clever. Religious opposition to Darwin was furious, and he was accused by Henry Triman, the botanist, that the threat he had posed to the doctrine of the creation was so powerful that the Origin of Species had made Darwin the most dangerous man in England. Tensions on this matter came to a head during a notable debate at the British Association in Oxford, during which Bishop Wilberforce attacked the theory of evolution, which was successfully and effectively defended by Huxley, who was at the height of his power. Indeed, Huxley remained a staunch defender of Darwin, and at a later public encounter with Bishop Wilberforce was reported to have informed the bishop that he would rather have an ape for an ancestor than a man who used his reason and intellect to attack those seeking the truth. The incident apparently caused an audience member to faint, and Huxley's following scientific arguments, combined with this comment, led Wilberforce to silence. Darwin later jested to Huxley, "How durst you attack a live bishop in that fashion?" Similar battles were fought between scientists and preachers across the world. In the US, Germany, and Russia, exchanges were held publicly between scientists and their opponents, bringing academics such as Ernst Haeckel to the fore, in a position similar to that of Huxley. Darwin attracted political as well as scientific attention. Karl Marx repeatedly tried to dedicate his book Das Kapital to Darwin, although this was rejected on numerous occasions. Darwin was later honored with a statue in the Soviet Union, which was used in part to spearhead a rejection of religious ideology. After 1859, Darwin published 10 biological works, 6 of which were engaged with particular botanical problems, dealing with questions concerning devices for securing cross-pollination, as well as the operation of climbing plants. One concerned earthworms and their effect on the natural environment, and the other 3 concerned themselves with evolutionary biology. Many of these later works were designed to augment and complement the theory that he had presented in The Origin of Species, although they also contained some odd digressions into theories of sexual selection. The first of these was the variation of animals and plants under domestication. In this work, Darwin turned his attention to the significant variation which existed amongst domestic animals and included dogs, cats, and foals, examining and analyzing the variation which they exhibited. He maintained from this his original conclusion that evolution was a slow process which relied not upon sharp variance between members of a population, but on small, incremental differences which became increasingly potent in a species over a long period of time. Later in his life, Darwin presented the theory of pangenesis, which was his attempt to examine and explain the ways through which characteristics were transferred between members of a species. He posited that something called gemmules were transferred between beings through sexual reproduction, a theory which was, of course, erroneous, but which was nonetheless a valiant attempt to account for inheritance in the absence of any knowledge of DNA. Following his variations, Darwin worked on a new book, The Descent of Man, in which he sought to powerfully reject the idea that man had descended from Adam and Eve, and posited rather that they had developed over a great period of time through the process of natural selection. Darwin asserted that humans had descended from a form of ape-like primate which may have originated in Africa, a theory which remains highly supported by more recent research conducted by academics such as Broom and Dart and Leakey. Many critics of the time were outraged at what they saw as his assertion that humans had monkeys as their ancestors, which was not in fact what he was arguing, since monkeys were the product of a period of evolutionary development which had been concurrent to that of humans. Darwin led his investigation with an examination of the similarities of humans and apes, and noted the similarity of the formation and operation of some organs and musculature between them, as well as the similarities in brain structure. He also noted several vestigial characteristics in humans, such as the embryonic formation of a vestigial tail, and that some humans possessed what later became known as Darwin's point, which manifests as a thickening of the helix at the tip of the human ear, an evolutionary trait connected to the pointed ear tips of several primates. Darwin also emphasized that humans and primates shared not only physical but also emotional characteristics. He argued that apes demonstrated an advanced emotional maturity, which manifested itself in reason, imagination, and sense of morality. Although he emphasized that, whilst recognizable as a distant embodiment of human-like intellect, that of mankind was doubtless greater. Darwin also dedicated a great deal of the descent of man to the topic of sexual selection, and argued that much of the struggle in nature was for reproduction. Mammals attempted to win out over one another for sexual engagement through physical combat, which enabled them to reflect shows of strength. He argued as well that for many species, the size of the male was an important determining factor in the sexual freedoms it could enjoy, and noted this as a significant factor in the mating behavior of animals such as the sea elephant, sometimes called the elephant seal. In birds, Darwin argued sexual preferences and choices for members of a given species were more often determined by visual displays. Male members of many avian species were more brightly colored than females, and their mating behavior often commenced with a dance or visual ritual, which enabled the male to display their feathers and plumes to a female. Darwin noted this behavior was particularly significant for birds of paradise and hummingbirds. Some of these ideas have since been discredited, such as Darwin's general assertion that animals were polygamous. We now know that many birds engage in monogamous relationships, and there have since been biological distinctions made between social and sexual monogamy, which Darwin confused with one another. Indeed, we now also know that colored plumage on birds often acts to defend territory and intimidate attackers, as much as, if not to a greater extent, than it serves in determining sexual relationships. These omissions informed Darwin's further general assertion that sexual reproduction within a species was almost solely determined by the choice of the female in sexual partners. This view has since been discredited, and we now know that many of these rituals are in fact mutual in allowing both partners to make a decision. In the final chapter of his book, Darwin turned to the sexually selective practices of humanity and asserted that, in this case, selection was almost always made by men, who, he argued, would choose a female partner based on several characteristics, such as their figure and facial structure. He indicated that many fashions attempted to augment desirable characteristics amongst humans, and for men, fashion reflected wealth and social status, which informed the choice that women made. These theories are, of course, very much of their time, and have been subject to countless criticisms from social scientists, and indeed, there is an obvious omission of several fundamental aspects of human social and sexual engagement, such as the importance of the formation of emotional bonds between sexual partners, and the fact that female choice in human sexual preference has been a constant throughout human history. Darwin's theory was important for the fact that it introduced the concept of displays as a form of choice information in sexual preference, although the field has advanced significantly in the intervening years. Emotions and their development were also of interest to Darwin, who noted that primates and humans shared several emotions and had a similar reaction to emotional stimulation, such as public shaming, and that both expressed more complex emotional responses, such as a desire for deliberate revenge when wronged. He pursued this field of study with his 1872 book, The Expression of the Emotions in Man and Animals, in which he studied how emotions were expressed physically by certain species. He noted with interest the expressions of emotion in cats, horses, monkeys, and apes, as well as a plethora of other animals such as porcupines, hyenas, and kangaroos, leading him to conclude that emotional expression was innate to many animals. In his pursuit of data on genuine emotional expression in humans, Darwin focused his attention on the expressions of infants and inmates in asylums, obtaining photographs of facial expressions which he labeled and analyzed, concluding from this, and a study he conducted internationally, that despite culture and region, human emotional expression was largely common across the world, and many behaviors and modes of expression would be recognized between humans wherever they were from. Darwin further argued that these forms of emotional expression, as they occurred in animals, stemmed from a preparation for action. Swans demonstrating a state of anger with arched wings and two-footed propulsion. Dogs baring their teeth in distress, which stemmed from an evolutionary practice of preparing for action, and thus giving animals with these displays of emotion an advantage in their prospects of survival. Darwin also dedicated later books to the development of vegetables and plants, and argued against a prevalent view that some plants engaged in self-fertilization. The variation which existed in these species would have to stem from some degree of cross-pollination, which he wanted to further investigate. Some work had already been done on the subject, notably by Christian Conrad Sprengel, who had advanced the theory that flowers attracted bees and thus played a role in the process of reproduction and cross-pollination in his 1793 book Das entdeckte Geheimnis der Natur im Bau und in der Befruchtung der Blumen, which was groundbreaking work in the development of biological understanding, but received little acclaim during the author's lifetime. Darwin wished to build on this understanding through research which analyzed the reproductive processes of plants and the process of cross-pollination. He studied orchids in particular and the ways in which the proboscis of moths had developed to obtain the nectar contained within them. One genus he studied was the Coryanthes orchid, which was structured in such a way that bees would tumble into the center of the flower and become covered with pollen, which once they had crawled out, they would spread to other plants. The various and ingenious ways in which plants were adapted to the process of cross-pollination was a source of immense interest to Darwin and led him to describe them as beautiful adaptations which could transcend in an incomparable manner the contrivances and adaptations of which the most fertile imagination of man could invent. Darwin examined these processes further in his later book, Effects of Cross and Self-Pollinization in the Vegetable Kingdom, which argued that there must be some innate value in the cross-pollination of vegetables, and that over time plants and pollinators such as bees become suited to one another through features such as the development of an elongated proboscis or a flower which allowed access to a certain species of bee. Darwin also advanced theories on the growth of plants and indicated that stems had the capacity to bend as they grew through the process of asymmetrical growth on one side of the stem, overtaking the rate of growth on the other side and thus pulling the plant around a curve. This process was often seen in plants which adapted themselves to make best use of light conditions, although it was a process which also took place at night, indicating that mechanisms beyond the reflexive response to light must play a role. Darwin's last book was produced in 1881 and concerned earthworms. He conducted much of this research in his home in Down House and erected a worm stone so that he might record the rate at which the stone descended into the earth, and thus how potent the influence of earthworms on the structural integrity of the soil in the lawn was. He conducted further experiments which allowed him to write about the anatomy, habits, and physiology of earthworms, and even analyzed the effect that music would have on their behavior, noting that a bass note played on a piano would send them into their burrows. Darwin, now late into his life, demonstrated that earthworms had caused the monoliths at Stonehenge to sink and thus appear far shorter than they were. He also showed that their actions were responsible for a Roman villa sinking so deep into the earth that it was too submerged to be affected even by invasive agricultural practices such as ploughing. This thesis, a little-known work by a man who is best remembered for his other research, nonetheless encapsulates the doctrine which was central to much of his work, that small, incremental actions and processes would, over time, come to have significant effects on the natural world. In the winter months of 1881 to 1882, Darwin experienced serious heart problems and was incapacitated more completely than he had been already. In February 1882, he wrote in a letter to a friend that he believed his course was nearly run, and on the 19th of April, he died, a short time after his 73rd birthday. Darwin was buried in Westminster Abbey and was carried to his grave by the President of the Royal Society, Huxley, Hooker, and Wallace, as well as several other notable persons, to be buried alongside Isaac Newton. Darwin was notable in his life for many things. The fact that a man with no formal scientific training would complete a voyage as testing as that undertaken on the Beagle, to then introduce one of the most powerful and influential models of biological development in human history, as well as a wealth of other botanical, paleontological, and geological theories which were groundbreaking in their own right, was truly remarkable, and he is today celebrated as the father of numerous scientific branches. The influence of Darwin's central theory of evolution cannot be overstated. The disruptive effect that this had on biological, scientific, religious, and social understanding remains truly significant across the world today, and he is often celebrated as a paladin of reason and scientific pathfinding. Darwin was characterized in great part by his humility, his dedication to his self-appointed task of scientific advancement, and his insatiable thirst for knowledge. We undoubtedly owe our modern understanding of our own origins and existence to him, and he remains one of the most celebrated scientists ever to have lived. What do you think of Charles Darwin? Does he deserve his reputation as one of the greatest and most influential scientists who has ever lived? Or should some of the credit for the theories of evolution and natural selection be at least in part shared with largely forgotten figures such as Alfred Wallace? Please let us know in the comment section. And in the meantime, thank you very much for watching.
In 1650, the Archbishop of Armagh, James Ussher, published a book entitled Annales Veteris Testamenti, meaning Annals of the Old Testament. One of the arguments in it is famous today, for it was here that Ussher dated the world to 4004 BC, by adding together the genealogical information found in the books of Genesis and Exodus in the Old Testament. Ussher's claims became the basis for the idea of creationism. Ussher, though, should not be viewed as a crude anti-science theologian. He was actually an extremely intelligent and well-read man. The problem was that humanity's scientific knowledge was underdeveloped. Ussher's chronology, after all, was produced 37 years before Newton's Principia was published and over 2 centuries before Darwin finally published On the Origin of Species. Scientific knowledge is accretive, meaning that it builds on itself. Newton built on Copernicus and Galileo, and people like Darwin and Russell in the 19th century were in turn building on the scientists of the 17th and 18th centuries. In the process, the flawed views of otherwise prolific scholars like Ussher were dismissed, and modern science emerged. This was a process that took hundreds of years and involved thousands of remarkable scientists, but from among those, there were always true giants, the few dozen people who revolutionized our understanding of the world. Isaac Newton and Charles Darwin were 2 from this small group. It was for that reason that Darwin, when he died in 1882, was laid to rest in the nave of Westminster Abbey alongside Newton, 2 pillars of England forever immortalized in Scientists' Corner.